All right, so here we go. Last part of this particular problem. Question is, how much farther would that projectile go if it was launched at 60 degrees above the horizontal? So we can actually do this without doing too much drawing. We'll just take information that we kind of already had and add it in. So new scenario looks like this. Same projectile, so launched at 50 meters per second, this time at a higher angle, 60 meters, or excuse me, 60 degrees above the horizontal. So if we do our components again, we've got the horizontal component, we've got the vertical component. Make a nice little triangle out of them. So horizontal, again, we can find velocity, range, and time. And we'll just use a little trigonometry to find the the horizontal speed. So if this is 50 meters per second at 60 degrees above the horizontal, again, this is the adjacent leg to that 60 degrees. We would use cosine, all right, to find what that leg of it is. So cosine of 60 degrees equals the adjacent over the hypotenuse. Multiply both sides of this times 50. That cancels that. So 50 times the cosine of 60. It turns out the cosine of 60 is 0.5. So if you do 0.5 times 50 meters per second, you get 25. All right, so the horizontal speed of this projectile is 25 meters per second. Now, if you go back to our original, right, you'll note that when it was at 30 degrees, the vertical component was 25 meters per second, and the horizontal was 43.3. So guess what? In this one here, since now 30 degrees is up here, all we've done is we've taken our original velocity triangle and we set it upright. So when we look at the initial vertical velocity, it's the opposite of 60 degrees, and there's our hypotenuse. So we'd be using sine on this one. So if we did 50 meters per second times the sine of 60 degrees, the sine of 60 degrees is like 0.866. Take it times 50, and we get that initial vertical velocity of 43.3 meters per second. And since it's going up, we'll define it as negative, as always. And again, just me, but I like my, gravity accelerates things or makes things go faster when they're falling, and it slows them down when they're traveling up. So that's why I always define down as positive. I feel like I've said that a time or two. Now, this projectile is going to follow this parabolic arc. And on the other side, it's going to come downward. And just before it hits the ground, that moment of impact right there, it's going to be traveling 50 meters per second at 60 degrees below the horizontal. So over there is horizontal component still going to be 25 meters per second. And its vertical component its downward component is going to be 43.3 meters per second, the mirror of what it was on this side. So the final vertical velocity is going to be 43.3 meters per second. Acceleration is due to gravity. So 10 meters per second per second. So we use that nifty little trick I showed you at the end of the last video. Where we take that equation right there, final velocity equals initial velocity plus acceleration times time. We've got the final is 43.3. The initial is negative 43.3. Again, just talking about all vertical stuff here, just ignoring the horizontal. Gravity accelerates things at 10 meters per second squared, and it's going to be multiplied by time. So if we add 43.3 to both sides, we get 10 times the time is 86.6. Divide by 10. By 10. The time that it's in the air is 8.66 seconds. Now, that's the total time that it's in the air. Bring that over here. That's the same on the horizontal side. So if we want to find the horizontal distance, we just do horizontal speed times time. So 8.66 seconds times 25 meters per second. That's 30, that's 33, carry the 3. That's 43. 2 times 6 is 12, carry the 1. That's 13, carry the 1. That's 17. 0, 5, 6. That's 11, carry the 1, that's a 2. 2 decimal places over. Holy smokes, the range is 216.5 meters. Just like it was over there. If we launch this thing at 60 degrees at 50 meters per second, it goes just as far horizontally as it did when we launched it at 50 meters per second, 30 degrees above the horizontal. It turns out if you take complementary pairs like that, 2 pairs of angles that add up to 90 degrees, they both will have the same horizontal range. And what it comes down to is on this one here that had the lower angle, it had a pretty good horizontal speed. All right, so it was moving left to right fast, but it wasn't overcoming gravity very well relative to this one. So this one had a greater vertical speed to start with when we shoot it up high. So it's doing a great job of overcoming gravity, but it then sacrificed the horizontal speed to do that. And you could do this with any 2 pairs of angles. If we'd said this one was at 20 degrees, then one launched at 70 degrees would land in the same spot. If you had one that was launched at 10 degrees, having another one launched at 80 would land in the same spot. So 2 angles that add up to 90 degrees, if the projectiles come down to the same height from which they were launched, they'll land in the same spot. They'll have the same range. Now, if you take that logic and work backwards, there is an angle for maximum distance. One where you're going to maximize vertical and horizontal the best you can, and it's right in between the horizontal and the vertical, 45 degrees. If you shoot something at 45 degrees, if there's no air resistance, you're going to get the best possible range that you can get from it. That's it.